So thank you for coming for our third installment of Catalysts of Change. The idea behind this lecture series really started with the idea of what are the big scientific enterprises that are really going to have an impact on your lives and the future generations. So today we're going to have a really interesting talk about data science and artificial intelligence or machine learning, and how we started with, I guess the word robots came from a Czech word about 100 years ago, and now we're at a point where robots are actually kind of interacting with you on a daily basis in some form or fashion. So we have this interesting experiment that we're trying to have two lecturers at once. So I'm really proud that we can invite Carlos Scheidegger and Stefan Kobourov to talk about the perils and futures of machine learning. Carlos was born and raised in Brazil, and he got his PhD from the University of Utah. And he developed a novel software system which allows scientists to this day learn to collaborate better and more effectively. He came to the University of Arizona in 2011 and is working on large-scale data analysis. Stefan Kobourov completed his undergraduate degree in mathematics and computer science, Greek and Roman studies at Dartmouth. He has a PhD in computer science from Johns Hopkins and is an expert on algorithms. He won the Alexander von Humboldt Fellow in Germany, and he also is a distinguished Fulbright Chair in the Czech Republic. So please join me in welcoming Carlos and Stefan.
Thank you, Elliot. All right. Thank you all so much for being here. It is truly an honor and a privilege. I want to start you in on a little secret that people who really work in this area will know. You see all these names: artificial intelligence, deep learning, machine learning, ML. What do they all mean? And the secret is that we actually have to use these for when we're talking to different people. You see, when we're talking to our graduate students, who are actually the ones that do all of our work, we call it neural networks, because that's what the computers actually do. When we're talking to other professors and we want to sound really smart, we call it machine learning, because that looks really fancy and smart. But the truth is, when we're talking to investors, to venture capitalists, then we really need money, and we need to sound really visionary. And that one we save artificial intelligence for. And so in this beautiful Tucson evening, Galileo Circle, I want to welcome you all to this really exciting talk about artificial intelligence. And please come talk to us later.
I can summarize the catalyst of change for artificial intelligence with 3 words: faster, cheaper, greater. Computing has become faster, storage has become cheaper, and the data that we work with is much greater than we used to. But for reference points, consider the Apollo 11 computer. In the year 1969, we put a man on the moon. A small step for man, a giant leap for mankind. And then consider the computer you have in your pockets. The Samsung Galaxy is the most popular phone, and perhaps many of you have it. There's billions of them out there. And consider what has changed in these 50 years. It is 2,000 times cheaper, it is 100,000 times faster, and it's 3.5 million times greater storage capacity. This is a giant leap for computing and a huge impact for artificial intelligence and all of our lives.
So these all changed entirely how we use computers, but there's one thing that really hasn't changed as much. And that is that actually writing code is quite difficult. Writing software today is easier, but not by much, than it used to be in 1969. So this is a picture of Margaret Hamilton, who was the lead programmer on the Apollo program. And so not only was it difficult because you had to sort of crawl in and actually install your software there, but this is a printout of part of the documentation for the Apollo lander. And so you see it was taller than her, and it hasn't gotten much easier today. We write that much more software. So it's still today quite difficult to write code. And it is tremendously expensive. So in 2013, it was estimated that sort of humans spent $312 billion a year in debugging software. Debugging means fixing problems. Means we wrote the code once, we didn't get it right, and then we need to sort of change it to fix the problems that we're making. That accounts for 50 cents out of every dollar that we spent on actually writing software. So it is really hard and is really expensive. And that's really where machine learning and artificial intelligence, in truth, come in. We want to use all of our bigger, faster, and sort of more powerful computers, but it's really hard to make them do the things that we want. And this is where machine learning really holds this biggest promise.
So let's think about how humans learn. We learn by examples. We hopefully listen to our parents and our teachers when they tell us what to do. Wouldn't it be great if instead of having to solve difficult problems such as landing a tiny piece of equipment on the moon and bringing it back, if we could just show many examples to our computers, and they automatically learn how to do the right thing? This is the promise of machine learning. Now, a science fiction writer who unfortunately passed away used to say, reality is frequently inaccurate.
So we like to think of ourselves, or at least professors do, as, we come here and we give lectures and everyone learns exactly the lesson that we intended them to, right? We like to tell ourselves, there's no way that they're going to sort of learn the wrong things, right? But the truth is that computers are really much more like children than when we're using machine learning than they are these sort of perfect students that learn everything. That means that you curse in front of them once, the moment you leave the room, you better believe they will have learned that thing. And it's not great. And in reality, this is really the problem with machine learning, is that it learns not what we wish it would learn, but it learns truly from what we show and what we do as humans. And here is the main problem, is sort of, you probably heard in the media, sort of, or in our stories and our science fiction, the robots will come and sort of, they'll become more intelligent than us, and they will sort of engage on this war, and then they wipe out humanity. And that's sort of science fiction. That's a sort of a stories that we tell ourselves because we're afraid of the outcome. The reality is much more complicated. The real problem is that machine learning learns from us. And at best, we are great. But at worst, we're a society that is still full of racist behavior, full of sexist behavior, and we are now sort of teaching these machines implicitly through the data. And so our problematic past and our present are truly the things that we have to wrestle with, and we need to learn how to not make our machines do. And in order to do that, we really should understand better how automation works, because that's what we're leading for. We're sort of hoping to automate our decisions about the world. And so this idea that we want sort of machines that can automate our decisions, that can automate our thinking, is not something that happened 50 years ago. This is something that humanity has thought of and fantasized for millennia, and that is really what Stefan will tell you all about.
A long time ago, in a galaxy far, far away, oops, wrong legend. A long time ago, on a Greek island, lived a giant by the name of Talos. Talos was made out of bronze. He was commissioned by Zeus, who was the CEO of the Greek god corporation. And he was built by Hephaestus, who was the engineer in the god corporation. And the job of the Greek bronze giant Talos was to patrol the island of Crete 3 times a day, mind you, and hurl boulders at invading ships. Some of you may remember the story of the Argonauts, Jason and Medea. Talos came to a sticky end at the hands of these guys. But a bit later on another island in the Mediterranean, a legend came about a king/sculptor by the name of Pygmalion. He created a sculpture out of ivory so perfect that he wanted it to come to life. Luckily, Aphrodite, also known as Venus in the Roman gods corporation, helped by bringing it to life. And unlike Talos, Galatea and Pygmalion lived happily ever after, and motivated many novels, plays, and movies, quite recent, some of them. And you're thinking, is it only the Greeks and the Romans who were dreaming of automation? No. If you look around, for example, in Jewish folklore, you will find the story of the golem. Don't confuse this with the Lord of the Rings golem. The golem is a creature you put together out of clay, and you animate it by saying the right words. Hopefully, you can disanimate it by saying another set of right words, and it goes back to clay. But in the meantime, it does your bidding. It took a long time to go from mythology and folklore to actually building machines that look and behave like humans. One such example is a machine built by Leonardo da Vinci in 1495. He called it Automa Cavaliere, or automatic knight. And the Vitruvian Man design, measuring human proportions, was used to make this automaton as perfect as possible. It could sit down and stand up, it could raise its visor, move its arms independently, and it was very lifelike. As Elliot helpfully mentioned, I have very carefully avoided saying the word robot, because this word doesn't come until 1920, exactly 100 years ago. And this word appears in a play by a Czech writer, Karel Čapek. The story is called Rossum's Universal Robots. I recommend it as an entertaining reading. Science fiction from 100 years ago. The word robot originates from a Slavic word which exists in Russian, Bulgarian, Czech, and other Slavic languages. The word is the word for work, rabota. So Karel Čapek gave credit to his brother for actually coining the word for the machine, robot. Now, if you're curious about what happens to the robots were created to help solve mundane tasks, and of course, they wiped out humanity as a byproduct. Robots of today seem different. From the most recent Consumer Electronics Showcase 2020, these two robots made a lot of waves. The robots that meow at dining customers were popular, as was the Charmin robot that delivers toilet paper when you need it. But joking aside, automation and robots are with us today. There's robot surgeons. There are unmanned aerial vehicles patrolling skies. Robots have been building our cars for a long time. They are trying to learn how to do bipedal motion, which used to be a challenge. Some of you remember 3 years ago, they kept falling. Now they can walk, run, and even do flips. And one of the difficult things for robots is to navigate a house environment, go upstairs, open doors, close doors, move things in the kitchen. This is happening too. And many of you are thinking, but wait, I haven't interacted with any of these robots, neither the Charmin toilet bot, nor the one that lifts cups from my kitchen. But you have interacted with bots and apps. In fact, you're interacting with them every day. Facebook is using the same technology in software to recognize faces of people and identify them. Amazon is analyzing your purchase history and predicting when you're likely to order something so they can pre-deliver it to a warehouse close to you, so the one-day free delivery will bring it there on time. Netflix is analyzing your viewing history and recommending movies and TV shows that you may like. Google is tracking your every move on the internet, and the result of this is that you're chased from web page to web page by running shoes, if you're me, or by handbags, if you're my wife.
Ouch.
And many of you interact with this machinery by talking to it. Siri and Alexa have made natural language processing a reality. Now, let me give you one very concrete example. On the highways of Arizona, you may encounter trucks that look like the truck in this picture. They have a logo on the side that says Embark. Embark was a company started by a 23-year-old guy, Alex Rodriguez, a couple of years ago. And let's hear what Alex has to say about it.
Everyone agrees that the only way that we're going to get to zero highway deaths, which is everyone's objective, is to use self-driving. And so I'm sure you've heard the statistic, more than 90% of all crashes have a human driver as the cause. And so if you want to solve traffic fatalities, which in my opinion are the single biggest tragedy that happens year after year in the United States, this is the only solution.
It's an ambitious goal, but only possible because of the recent breakthroughs in deep learning.
Artificial intelligence is one of those key pieces that has made it possible now to do driverless vehicles where it wasn't possible 10 years ago, particularly in the ability to see and understand scenes.
I hope you're impressed. In the words of a 21st century science fiction writer, the future is already here. It's just not evenly distributed. We are living in the future. Now, you can think of it slightly differently. The New York Times had an animated GIF that summarized the idea of automation like this. My interpretation is, be ready, AI is coming for you and your jobs. But how does all of this work? What do these terms, artificial intelligence, machine learning, deep learning, mean? As Carlos mentioned, at the core of it all lies the concept of a neural network. And I will try to explain a little bit about how all of this works. The idea of neural networks is old. In the 1940s, people studying how brains work, our brains, came up with the model that the brain is made out of millions and billions of tiny little cells called neurons that talk to each other. They receive signals and they pass some signals on to their neighbors. In particular, McCullough and Pitts, when they were working with this model, called it nervous nets. I like this term because it still makes some of us nervous about this thing being in our brains, or worse, this thing being in our phones and our laptops. But what they realized in the 1940s was that this model is powerful. A good model for a complicated system is one that makes simple things simple and complex things possible. And the surprising thing that I realized was that you can make very complex things work with a very simple model like this. In fact, they realized that the neural network seems suspiciously similar to an electric circuit. This picture on the right side of the slide is from their paper, and this looks like electric circuits. And indeed, it took another decade for somebody to realize this idea in hardware. The Mark I perceptron built by Frank Rosenblatt made artificial neurons and connected them with wires. And the input to the real cells in the brain or to the artificial neurons on your computer is a set of signals that come in. There is a function, you can think of a simple function that adds them together, and if they exceed a certain threshold, if the signal is strong enough, they pass this information on. This is the machinery behind our brains and our artificial intelligence. Now, there is a difference. Real brains are big. There is estimated to be about 86 billion neurons in a human brain, whereas a typical neural network has significantly fewer of them, on the order of 100,000. And there's a difference. The real neural networks are complicated and messy. Computer scientists like to bring order out of chaos, and so our neural networks look like this. Even though it's a schematic, it's much more regular and organized. And now you're thinking, a lot of words have been said, 20 minutes have passed, I still don't know how neural networks work. Fear not, I will try to explain. And I will try to explain it with a hypothetical problem that we'd like to solve with the help of artificial intelligence and machine learning. The problem that I will try to solve is the PhD admissions process at the computer science department at the University of Arizona. I have been at the department for 20 years, and the department has existed for 49 years. And every year, a large fraction of the department gets together and analyzes a lot of applications for students who would like to become PhD students in computer science. And we always worry, did we do a good job? Were we too subjective? Did we do a fair job solving this problem right? How about we create yet another AI CS PhD admissions app, Ickes for short. The purpose of this application will be to use artificial intelligence to determine whether to accept or reject a particular candidate. Now, how is this going to work? It's going to work by analyzing past data, 49 years worth of data that the computer science department hopefully has stored somewhere, and try to make predictions about the future. A new candidate comes in. What can I learn from the 49 years worth of data to predict whether this candidate is likely to succeed or fail? Now, this idea of using past data to predict the future, even though financial companies like Fidelity and Vanguard warn you about not using, past performance does not predict future behavior, this is something we have been using for a long time and will use for a long time in the future. Betting works on these principles. So does political election predictions. Analyze the data we have from the past and try to predict the future. So let's talk about Ickes. Ickes has a simple goal. Evaluate the quality of each applicant and decide whether to accept or reject them. Now, what individual features will we examine to make this decision? We can examine things like the GPA, their scores in their bachelor's program. We can examine their graduate record exam verbal score, or their graduate record exam quantitative score, or their graduate record exam analytical score. We can also look at whether they have a relevant major or not. For a computer science PhD, a relevant major would be something like computer science, or math, or statistics, but surely not Greek and Roman studies. We also like to look at, do they come from a good school or not? We may want to look at, have they some research experience? Have they participated in a project and maybe published a paper as a co-author? So how do we define quality in this goal? Quality, like love, is in the eye of the beholder. For some of us, the quality of a candidate is the likelihood to perform groundbreaking research. For others, it's the likelihood to become a great teacher or a great professor. For some, perhaps those in the university administration, is the likelihood to become a tech millionaire, so you can donate a lot of money to the university so we can run the university instead of as a business, as a university. But But as it turns out, for many applications, including this hypothetical one, what we're going to use is something that is actually easy to measure. The previous three that I gave you are great, but very difficult to measure. The last one, the likelihood to obtain a PhD in 6 years, we can measure given 49 years worth of data. So let's proceed further. What does evaluate mean? Perhaps some of you give scores to your purchases on Amazon. Perhaps few of you receive scores by your Uber drivers. We are familiar with the concept of assigning scores to things, whether they be objects we buy or humans. Some of us have credit scores. Some of us have number of points on our driver's licenses. This is all the same issue. The goal of this exercise is to assign a score so that high scores should be correlated with high quality. Not always true, but we can dream. What does learning mean? Finally, we get to the most important word in this goal: learn to evaluate application quality. What we need to do is to determine which features were most important. How important was each feature? Was the GPA important? Was the GRE quantitative score important? Was it the research experience that was important to determine success? We may want to consider not just individual features, but combinations of features. Perhaps 3.75 GPA from MIT and a 4.0 GPA from ASU have different impacts on the likelihood of success. Most importantly, learning here means solving a math problem. And I will try to show you what the math problem is by example. Let's try to put all these bits together. Hopefully, we don't end up with a paradoxical chair or table from IKEA. In principle, it sounds straightforward. Given a bunch of inputs for every candidate, GPA, GRE, school, given a definition of quality, the likelihood to obtain a PhD in a certain number of years, given a historic data, 49 years worth of data, given the notion of evaluation, high score should correlate with likelihood of success. Learn to combine all of these inputs to predict success. And here's Ickes v.1. Ickes v.1 looks at the data. Now you get to see the data. 49 years worth of data that looks like this. There's many columns. Every column is a PhD student in the computer science program. And the first 7 rows you recognize. These were the statistics, the data inputs associated with each candidate. The last one is the one that we haven't talked about very much. Because this is historical data, we can look and discover that Ajit, with all of his statistics, succeeded. He obtained a PhD in 6 years. Blake, with all the statistics associated with him, did not. Cedric did. Daniela did, and so on. So version 1 is usually not very good. Let's try with a not very good idea. How about we just look at one number for every candidate? After all, that's why we're paying to the GRE Corporation. Let's use the GRE quantitative score and look at the data and figure out what number is the best number that fits the data. Higher than this, you should accept. Lower than this, you should reject. Now, I see some people shaking their heads, even though I don't have my glasses. You know that this is not likely to work. And indeed, it doesn't work. GRE scores, whether quantitative, qualitative, analytical, even subject, do not predict school success. What does? Here comes Ickes v.2. Now with more features. We have 7 features. Why are you just using 1? Let's use all 7. All right. So let's analyze the data, 49 years worth, and try to figure out what parameters, what weights to give to each of these features so that it fits the past data as well as we can. And indeed, version 2 may produce something that is better than flipping a coin. I haven't tried it, I don't know, but it's possible. It's good to think about what was learned by this machine learning system. This is a machine learning system, and you are improving it with me. What does this machine learning system learn? It learned 7 parameters. This is what the system learned. Version 3, new and improved. Something changed from version 2 to version 3. Oh, yes, I've added a hidden layer. Here it is, these 3 boxes that have no labels on them. This is the hidden layer. What does the hidden layer allow me to do? It allows me to finally realize that 3.75 GPA from MIT might be better than 4.0 from ASU. How? Because I can use one of these unlabeled boxes to combine pairs of inputs. So I can also learn other features which I expect to be true, that a low GPA but great research experience as an undergrad is better than great GPA and no experience, no research experience. What are we learning here? What is the machine learning system learning here? It is learning 24 parameters, more than before. And the accuracy is likely to improve. Version 4, now with more hidden layers. If one hidden layer was good, more hidden layers are surely better. More hidden layers will allow us to learn more complicated patterns. And in fact, some of you may remember, Alex Rodriguez, the CEO of Embark, used the phrase deep learning. And deep learning does not refer to deeper thoughts, or deeper knowledge, or deeper understanding of the problem. It refers to the number of layers in your network. This is deep learning. Now, this used to be expensive. The machinery to do machine learning of that type has existed for decades, but it used to be very expensive. But remember, just like Apollo 11, we performed a giant leap for computing. Now we can do it. What does this system learn? This system learns more parameters, 33 of them, and perhaps is more and more accurate and getting closer to being perfect. Yay, yikes. Carlos and I are going to start a company. We're going to call it Yikes Inc. And we're going to sell our apps to all computer science departments in the world with the slogan that it's more objective, there's no human involved. It's data-driven. Data-driven is good, right? And it's fair. Or is it? Let me mention just a few problems that Carlos will elaborate in a minute. Did I look at all of the data when I described this Yikes application? No, because the only data that we could have is the data of the students we accepted. But we rejected quite a lot more. And of those we accepted, not everyone accepted our acceptance. The data that we could look at to develop our Yikes application is a small fraction of the total number of applicants. I would guess 5%. Further, I don't know this for a fact, but I know it's true. An overwhelming majority of the PhD students in the 49 years of the computer science program at the University of Arizona has been male. And there's a bias that gets picked up when you work with biased data. Another problem that is fundamental, the system that I'm describing here does not learn the way the admissions committee made out of humans learns. If you ask Carlos when he was on the admissions committee, why did you reject this candidate? He will give you an answer. If you ask Yikes, version 1, version 2, version 3, version 4, it will tell you something like P1 equals 3.14, P2 equals 2.71, P3 equals 6.62, and so on. And now you're thinking, thank God they haven't built this application. This would be a disaster. But there are AI-based programs, just like the one I described, that look at applicants' resumes and decide whether to pass them on to a human or not. They work exactly the same way as the Yikes system does. There are AI-based programs that determine prisoner sentencing, bail determination, parole determination, that work exactly the same way. And many of you in the audience are thinking, wait, I'm not applying for a job in a high-tech company. I haven't been in prison recently. What do I care? Well, perhaps you have applied for a bank loan or a credit card. Guess what? It works exactly the same way. Each of you is a bunch of numbers your age, your gender, your income, whether you own a house, whether you own a car, your credit score. And the decision is simple: give or not give. The bad news is that many people get denied a credit card or a bank loan because of a system like this. The other bad news is that some people get approved. And you end up buying another car and another house that you don't need. Now, it's not surprising that you can use the same machinery to decide whether to buy stocks or not. It's not surprising that this can also be used for important issues such as health and medicine. Imagine every human is associated with a bunch of data: age, gender, race, DNA profile. We can use this data and analyze it and realize that I am more likely to respond to a specific drug, and Carlos is more likely to respond to another. We can use the same type of analysis to realize that some of us are more susceptible for one disease than another and catch it before it happens. The U of A is part of one of the largest precision healthcare programs in the world. And this is all good.
So are you telling me that all of this is just like Ickes? This is your machine learning system?
Yep. Almost all of it works the same way. You pour some data in, you do a little algebra, and collect the answers at the end.
But what if the answers are wrong?
Oh, just stir the pile a bit until they're right.
And here's another secret. This is actually really how this works. And so this has been 30 minutes, but Stefan is, actually an excellent teacher, so you're all now experts in AI. This is truly how this works. So now we are all capable of opening the black box of AI and seeing what's possible. And so that's what I want to tell you a little bit about. So you're all here to sort of hear us tell you about the promise of artificial intelligence. And it is certainly the case that so many amazing things are possible, and I want to tell you about some of these. I want to start telling you about a work that is done by a colleague of ours, Jason Pacheco, who just joined our department as an assistant professor. This was work that he did in his postdoc at MIT. And so this was a work where they were using data that came from an implant from the motor cortex from patients that were fully paralyzed from the neck down. So these are patients with tetraplegia. And it turns out that by putting the right amount of machine learning on the data that is coming out of that device, you can actually learn how the person is thinking. And so these people who are entirely paralyzed from the neck down, they only have sort of muscle movement this way up, they now actually can recover some amount of control over external devices. So this is a video that I'm going to show you of the system actually working. So just to give you a little bit of context, the patient is in the bottom here. You can see the device there. So this is actually implanted, and it's reading data from their cortex. And what's really amazing here is that that screen is connected to the system that's learning this. So that white dot there is the cursor. What you're going to see is a red dot, which is the target for this. And so the patient is going to move the white dot towards the red dot by imagining that they're moving their limb. So they're imagining that they're moving their arm towards where they want the cursor to go. And we can use machine learning to learn the signals of the brain and actually make this happen. So that cursor there is literally being moved by the mind. So this person who is completely paralyzed and does not have movement of the arm is thinking of that arm moving in the right direction, and we can use that to completely change the kinds of devices that this person can use. So you can imagine that today we can use this to drive a mouse cursor so they can actually use the internet. But you can imagine in a few years you can use this to sort of create devices that will give these people mobility, and machine learning here is being used to sort of quite literally read people's minds and sort of understand the way that our brain works. This is the promise that machine learning can get. It can be so incredibly empowering for people who are otherwise less able. But we can do much more than that. So Stefan told you about our deep learning Ickes system that had 2 layers. It turns out our computers are so fast today that we can build these neural networks with hundreds of layers. So the current sort of state of the art from Google and from those places have on the order of 200, 300 layers. And it turns out that if you set it up in the right way, you can give these systems a great many number of faces on the order of millions. Imagine Google has access to all of our pictures anyway, so we can sort of get a large corpus of faces. And these neural networks sort of learn to imagine new faces. None of these people are real. These are all images that were imagined by a neural network. Essentially, these were images that were created by giving parameters and reconstructing the image back from them. You might say, no, you're lying to me. This is not possible. So what I'm going to show you now is a video in which we tell the network to slowly change one image to the other so that you can see all of these are truly imagined, including this one and all of those. So this is possible today with the computers that you all have in the home. Does not take more than a laptop and a few seconds to generate each one of these images. This is not supercomputing territory. This is possible today. Imagine this in the hands of an artist who is tasked to generate sort of new worlds for, a new movie or for an animation. And instead of having to do sort of the drudgery work of drawing all of these, the artist can imagine what they want to do, give it a large corpus of data to a machine, and it will learn to synthesize. So you can imagine this world in which artists work together with neural networks to create these incredible images. The problem, of course, is that the same technology that can be used for these amazing things can also be readily used for less amazing things. So this can also be used quite readily for disinformation and for harm.
To help families refinance their homes, to invest in things like high-tech manufacturing, clean energy, and the infrastructure that creates a good new job.
None of these are real. We can make Ronald Reagan speak the speeches of Obama by showing the sequences. We can make this
See,
too.
I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele.
So the video is being controlled entirely by the facial expressions of someone else. This is now possible, again, with your laptop. So because we have access to so many faces, the same technology that can be exceedingly powerful for an artist can also be exceedingly used for harm. This is not only to do with images. We can do much more than that. Let's say you are traveling and you go to a foreign country, and it happens to be a foreign country in which the script is entirely foreign to you. Now, if you're there by yourself, you're host. Perhaps you have a friend who speaks the language who came with you, and you can just go say, Stefan, I'm stuck. What does that say?
It says, Vojhod Garod.
Great, but that's not helping us much because we now know exactly what that sounds like and we still have no idea what to do with it. But perhaps you can have your phone on your pocket. And it turns out that because, again, we have so much data, we have so much compute power, we have the sentences in all languages. And we can automatically learn which ones line up to the other by using just data from the internet. Just using things that have been translated by other people, we can mine those and learn how to translate languages. Not only that, we can learn how to read those. And in fact, your phone does that today. So if you point your camera to a sign, it will not only read the sign, but it will actually print it back in English. So you will know that what Stefan said is actually how to make it to the city. This is possible entirely on your phone, right? Your phone today is faster than the fastest supercomputer that we could build in the world as of 25 years ago. That's how fast things are changing. So we can use all the data from the internet to enable these incredible things that essentially come for free for us. Of course, we took data from the internet, and text from the internet is biased, and so we give biased data in, we get biased data out. So this used to be actually live data from Google Translate, where if you used a language that has gender-neutral pronouns like Turkish, you would ask, translate, they are a doctor. It would choose to say, he is a doctor, as the translation in English. You would use, they are a nurse. The translation you get back is, she is a nurse. And this is coming from the fact that we are taking data from the internet. The internet has a problem with representations with respect to gender. This should be no surprise. But we are teaching our machines by the things we do, not by the things we wish they would learn from us. This is an endemic problem. It's not just about translations. This is fundamentally the problem that comes. Every time you hear someone saying, I have a fantastic problem that I'm going to use machine learning for, I hope you walk away with this one idea. You should think, where did the data come from? Who collected the data? No data is unbiased, right? Data is collected by someone for some purpose, right? We have to think about where is this data coming from? Who is using it? Who is it using it for? And in some sense, we shouldn't be surprised that sometimes all we get are the biases that we're in the first place. This is not only with translation. We are now using machine learning, like Stefan said, to make predictions about policing. And this is a particularly problematic area, and I want to read something about the first, this is an article, and I want to make sure I read the first paragraph. This is a work from Christian Loom and William Isaac. And so this started happening in the last decade, and I want to make sure I get this right. In late 2013, Robert McDaniel, then a 22-year-old black man living on the south side of Chicago, received an unannounced visit by a Chicago police department. The police commander warned him not to commit any further crimes. The visit took McDaniel by surprise. Why did the police come knocking? It turns out McDaniel was in Chicago's police hot list and had been forecast to be involved in potential future violent crime, even though he had no record of doing so. This is just data that we gave it, right? So in work that I was fortunate enough to do with colleagues, Sorel and Suresh, we've shown that these predictive policing systems, these systems that attempt to use data to make predictions about where to send policemen, they get sent into these feedback loops. They start sort of feeding on their own predictions. And the fundamental problem here is, like Stefan said, we would like to think of these systems as making predictions, but these systems are making decisions. They're telling us where to send the policeman, and those influence the future decisions. And when we do this wrong, we end up with policing that is completely unrepresentative of the distribution that we were hoping to send. It ends up being meaningless, and of course, it ends up over-policing minority neighborhoods. This is exactly the same problem that happens in other fields. When Amazon decided to scrap its AI tool that it was using for resume screening, it wasn't that it was directly using the gender from the name or sort of from anywhere in the resume. Most people don't even disclose that. It turns out that there's other information there that sort of leak the attributes that you would like it not to be influenced by. In their case, they learned that, for example, if your resume said that you were from Smith College or from Wellesley College, right, so these are women's colleges, the system had negative sentiment towards the resume. They found this in a very simple way. They just flipped that to say University of Arizona or something like that, and suddenly the resume looked a lot nicer. And that's problematic, right? That means that they were sort of repeating the past decisions that they made. This is the same thing that happens with credit cards, right? So when people who apply for credit cards don't get it, Amazon and Apple in this case said, we never use gender as a feature for us, right? Remember Stefan told you, these are the features, and then Apple says, we never really used this feature. Well, it turns out that as long as you can figure out that feature from the features that you do have, you still have the potential for this. And this is where these problems come up. But I want to come back to faces, and I want to show you that, some of these things are truly amazing. It's not all bad, right? We can use AI for incredible things. And your phones, as I said, they're really supercomputers. And some of the things that they do are quite subtle, but they're actually really nice. So for example, no one today takes a selfie that is out of focus. You might not have noticed this, but it simply doesn't happen. And the reason that it doesn't happen is that your phone automatically picks up your face. It just knows where it is, and it focuses there and makes sure that it doesn't focus on the saguaro that's behind you when you're taking the picture. It just does that automatically. It does even more. Your phone waits for you to smile. So when you take a burst picture, it actually waits for you to smile before it captures, because it knows that the memory you want from that picture is the memory of the moment of you smiling, not all the other pictures in which you were blinking. It actually stitches two people that might not have smiled at the same time. As long as both of them smile, it picks up the best part of each picture and gives you the memory you remember and not the image that you probably capture on those. It does that for you for free automatically. This is really good. This is the kind of thing that is possible if we choose to use it in that way, right? So that's good. It's not all great.
Hi, I'm Joy, and I research how computers detect, recognize, and classify people's faces. In my TED featured talk, I spoke about my experience with the coded gaze, my term for algorithmic bias. The system I was using worked well on my lighter-skinned friend's face, but when it came to detecting my face, it didn't do so well, until I put on a white mask. After my talk was posted, I tested my speaker image profile across different facial analysis demos. 2 of the demos didn't detect my face. The other 2, well, they misgendered me.
So think of these systems that are assuming, for example, a gender binary. This is the feature we chose to put there, and now we are harming people completely unnecessarily. Often we don't even need these. It gets even uglier. So this is work that came out a couple of years ago in which researchers claimed that deep learning, deep neural networks are more accurate than humans at detecting sexual orientation from facial images. The first thing to wonder is, do we have to? But let's say we're curious, we want to see, and then you should be skeptical. How did this happen? And it turns out that no, it didn't really happen. The data collection process is completely, you can explain it entirely. The data that they got for one of the cohorts was data from a professional social network. The other data was from a social network for dating for same-gender people. They took some data from Grindr and some data from Facebook. Shouldn't be surprising that people present differently, and that explains the result that you get. So no, we cannot do this, not even in principle. It gets even uglier. People now claim that you can use deep learning to detect criminality. So again, took some data. Here's a picture of these people. Those are people who we claim to be criminal. Those are people we claim to not be criminal. Again, should sort of, how is this possible? And no, it really isn't. When you read the work, the data collection was entirely to blame. They compared pictures essentially on professional social networks to pictures that are mugshots. Of course, these are taken on entirely different contexts, and these are pictures that are completely independent of whether or not someone can do this in principle. And if you're feeling uncomfortable about this slide, part of the reason is I want you to see that people are claiming that these things that are clearly impossible to do, somehow machine learning will do it. It's not. You cannot do this. In fact, this is no better than phrenology. And by the shape of your head, they could tell you whether you were likely to commit a crime or not. This is, again, entire pseudoscience. It was an excuse for essentially people to discriminate against certain ethnicities, right? And now we are putting all of this bias into our data sets under the guise of machine learning and hoping that it will work out. It doesn't. It really won't. And Stefan told you this really nice quote about the future being already here. It's just not evenly distributed. I want to sort of bring the different perspective from Faulkner that says that the past is never dead, and it actually isn't even past, right? Those mistakes that we've made in the past, they are not going away unless we really work at them, right? People are still trying to repeat them. We should be careful about those. So here is the main message that I want you to sort of take with you. And the message is that artificial intelligence is extremely, extremely powerful. It's fantastic. We can do so many incredible things. It does not exist in a vacuum. It uses the data that we give it to. And it reflects who we are. And so we should choose to give it our best reflections because it reflects all of it.
Indeed, we can choose what to do with artificial intelligence. Should we use artificial intelligence to sell sneakers and handbags? Or should we use it to cure cancer? Should we use it to recommend movies? Or should we use it to send people to prison or not give them parole? This is not a deep fake. Mark Zuckerberg, in the early days of the Facebook Corporation, had this as the slogan of the company. Move fast and break things is a great slogan if all you're doing is starting a new social networking company and you'd like to drive all the others out of business. MySpace, anyone? It is perhaps okay if you're recommending movies or selling sneakers. But it's a terrible idea if you are building self-driving trucks, or if you're building robot surgeons. So, we should be using artificial intelligence to help Chris guide unmanned missions across the solar system.
We have a choice. We could be using artificial intelligence to help the tool detect exoplanets. There's a lot of data there. We can use machine learning for those. We can choose to detect chemical signatures in the distant exoplanets that we now have the power to look for.
We should use artificial intelligence to identify endangered megabiota and help Brian from last week. And
like you're going to see next week in Howard's talk, we could also use artificial intelligence to identify harmful toxins such as aflatoxin and its carcinogenic qualities and safer food supply. We can use artificial intelligence for these things.
Having spent a year in Africa, I feel like I brought this African proverb with me to Arizona, but many of you have heard it. You can go fast and break things, or you can go far by traveling together with other scientists, with humanists, with philosophers, and ethicists. And I hope you all join us on this great journey to the future, which is already here. Thank you.
So I hope you enjoyed our evening today to learn more about deep learning, or I guess artificial intelligence, again to the people in the front. But broadly speaking, I hope you'll come back next week to hear Howard Shapiro talk about the future of our food supply. And as Brian mentioned last week, you know, it's our metabolism that's really the most important part. And how do we have that metabolism? It's by food. So we'll see you next week. Thank you very much.